Hello friends. So today I will discuss about the Maxwell equation. Probably you know that there are four equations which are known as Maxwell's equation. And number one is del dot E equal to rho upon epsilon naught, where rho is the charge density, E is the electric field, and epsilon naught is the permittivity of the vacuum. And this is nothing but the differential form of the electrostatic Gauss law. So electrostatic Gauss law. And if you look at the second Maxwell's equation, del dot B equal to 0, and the third one is del cross E equals minus del B by del T, and the fourth one is del cross B equals mu naught J plus mu naught epsilon naught del E by del T. So this, if you look at the second equation, this it has no name as such, but we can call it it is equivalent to Gauss law of magnetostatics. And third one is the nothing but your Faraday laws. The change in magnetic field creates electric field, and the last one is nothing but the Maxwell's modified Ampère-Circuital law. Maxwell modified Ampère-Circuital law. So here we can see that this is the Maxwell's original contribution to the fourth equation, because before Maxwell the Ampère-Circuital law was known in the form of del cross B is equal to mu naught J, where J is the current density, B is the magnetic field, right? And this was the Ampère-Circuital law before Maxwell. Before Maxwell. So now the question comes: how did Maxwell fix the Ampere's law by modifying it by a term? And how did he know that there has to be an extra term which has to be added in the Ampère-Circuital law? So his argument was quite mathematical, in the sense that if we clearly see, let's say, equation 3 from above, which is del cross E equals minus del B by del T. So you take the divergence of it. So divergence of the left hand side and divergence of the right hand side, if we see, so divergence of the curl is anyway 0, always 0, and therefore, and also in the right hand side you see del dot B, which is 0 from the second equation identically. So this is both the sides gives us 0, so no problem in this equation. But however, if you look for the fourth equation and take divergence of the fourth now, so what you see, that divergence reads something like this. uh, Remember, this was the only law. Del cross B is equal to mu naught J was the only form known to world before Maxwell's contribution. So if we take the divergence of this law, both side of this equation, both sides, so left hand side should read 0 because the divergence of a curl again, but right hand side, if we see, is not necessarily 0, because we know that from the equation of continuity, rho dot plus del dot J is 0, and del dot J is minus of del rho by del T, right? And rho is from the first Maxwell's equation, rho is equal to epsilon naught del dot E. So if we put here, so this is actually not exactly 0. Okay, it is a non-zero quantity which can be written as something like this. So it's a non-zero right hand side. Left hand side is 0, identically 0, but right hand side is non-zero, so it means there is something wrong with this form of Ampere law, or at least it is incomplete in some form, because we cannot say it's wrong because it was experimentally verified up to here. But there is some mathematical inconsistency which Maxwell fixed, because you see we get this much term in negative. So if we add by hand, from what did Maxwell do? Maxwell actually added the same term in the right hand side positively, so that this compensate the negative term that we get after taking the divergence. So this term will give me exactly equal and opposite in sign of this term on taking the divergence. So this is how Maxwell fixed this inconsistency of the Ampere-Circuital law. Now we can have a lot of discussion regarding the Maxwell's equations. Like first, other thing we can discuss is that what's the uh, physical significance of the first equation, del dot E equal to rho upon epsilon naught. It says that a possibility that electric monopole can exist, because it's the first equation says the divergence of electric field is not always zero. It depends on rho. If rho is zero, the charge distribution is absent, then of course divergence of electric field is zero. Otherwise, if rho is positive, we have a positive divergence. If rho is negative, we have a negative divergence. It means the electric field lines will emerge out of the space when, if you have a positive charge distribution, and electric field line will sink to the space where if rho is negative. So we can have a source and sink of the in the form of charges. Like we know that with electric field lines come they come out of the positive charge and this sink at the negative charge. Therefore we know that from our experience, previous experience, that the electric monopoles do exist. However, if you look for the second equation, which is del dot B equal to 0, net divergence of magnetic field is always zero, identically zero. That means no magnetic flux, net flux can come out of any space. That is, the number of field lines that is coming out of any space will be exactly the number of magnetic field lines coming into that space. So magnetic field lines actually form a closed loop. If you see that there is a magnet north and south, so magnetic field lines come out from the north pole and they merge at south pole, and inside the magnet they go from south to north. So they form a closed loop. No net flux comes out of it, and therefore we can say that the magnetic monopoles don't exist or can't exist, because if they do exist, so we'll have a positive or negative divergence of magnetic field, which is not possible. As I've already discussed, the third law is nothing but the Faraday's law, and the fourth law is nothing but the Ampere-Circuital law. Now, is there any way of we can interpret the physical significance of the term which was added by Maxwell, which is by the way is known as uh, displacement current, because this quantity here, epsilon naught times del E by del T, is equivalent to the having the units of current density here. So this is known as displacement current. Epsilon naught del E by del T. This is known as displacement current. So can we understand any application of this, or any use of this term? So in when we try to explain the problem of charging capacitor, suppose we have a parallel plate capacitor. We'll take the example of a parallel plate capacitor. The, we have a battery connected to it as a potential V, and this is a positive plate here, it's a negative plate here. So when the during the process, when the capacitor is getting charged, let's say I current is flowing through this, and if we take an Ampere-Circuital loop, Amperian loop here, so if we try to apply the Ampere-Circuital law, which is del cross B is equal to mu naught J, so we'll consider the current which is piercing through this Ampere loop. We have to always consider that current in Ampere law which pierces through the loop. So I current is coming in and I current is going out. So J is related, I is equal to J times A. If we have current density J and we have a cross section area A, J dot A is the I. So that's not a problem. So it's giving us some value of the magnetic field nearby we can calculate. But suppose if we take the Amperian loop of this kind. So red current Ampere loop, the problem with this loop is that I current is coming in but no current as such is going out. So we cannot put any value in the right hand side. It should be 0. But we have just seen that the magnetic field have a non-zero value by applying the Ampere-Circular law from the first loop, right? So it means something is missing in this Ampere law, which was before the Maxwell's, and let's try to see whether Maxwell's modification to the Ampere's law solves our problem or not, because we want to find out the B, and by choosing the second Ampere loop that we have taken. So in the second Ampere loop, as we say first term is anyway 0. What about the second term? So we have to see what the second term is. So we know that the parallel plate capacitor has the capacitance K epsilon naught A by D, and if the dielectric medium between the two parallel plates is the vacuum itself, so it's epsilon A by D. We also know that if V is the potential difference between the two plates and electric field inside the plate is E, and D is the separation between the two plates, so V is okay, C equal to epsilon naught A by D, and we know that E is equal to V by D. So if we take the current value dq by dt, and q is cv and v is ed, so if I take d del e by del t, now I can put the value of c, the capacitance. So equivalent current, I will have epsilon naught a by d times d del e by del t. So d cancels out, so epsilon naught a del e by del t, and I by a is j, so j is equivalent epsilon del e by del t. So if I see that the Ampere circular law del cross B is mu naught j, so this now my value will automatically turn out to be mu naught epsilon del E by del t, because j is this. So it means when we are dealing with this kind of Amperian loop, which is the second current, no current is piercing through it. However, charging is taking place, magnetic field, electric field is getting built up, and magnetic field is all this, because the electric field is changing with time, therefore magnetic field is also there. And to know the value of that magnetic field, we can apply the Maxwell's modified Ampere law, and then the second term gives us the exact value of the magnetic field which was there earlier, which was required. So this is how the charging capacitor problem can be seen through the Maxwell's modification, and the explanation fits very nicely. Now if we come back to the uh, equations again, like if we look carefully, the first Maxwell equation is a scalar equation. The second one is also scalar, but the last two are the vector equations. So since they are vector equation in 3 dimensions, so they have 3 components. This one is also a 3 component. So if you see carefully, so these are basically 8 equations: 2 scalar, 2 vectors, having 3 components. So 6 plus 2, 8 equations. So what is the objective of knowing Maxwell's equations? Why Maxwell wrote down? Because Maxwell wanted to unify the two different branches of physics, basically electricity and magnetism, and give a theory called electrodynamics. So whatever knowledge was there up to Maxwell's time, he was able to combine all knowledge in these 4 equations, and sort of gave us a unified picture of this larger theory called electrodynamics. Objective is always to find out the E and B, provided rho and J are given. So rho and J here are the knowns, and E and B are the unknowns. Rho and J are knowns, and E and B are unknowns. unknown. So our job is to find out E and B provided rho and J are given. But if you see, has three components: Ex, Ey, Ez, and therefore B also has three components: Bx, By, Bz. So basically we need to find out six quantities to fix E and B, and we have eight equations. As I just discussed, it is a scalar equation. One equation comes from this, one equation comes from second, and three equation comes from this, and three equation will come. So eight equations are there, and six are unknown. So this clearly means that we have larger number of equations than the unknowns. Therefore, there are two possibilities: either some of the equations are redundant, that is they don't give any extra information, or maybe there is no solution for that. But we have seen that all these four laws are very well verified, physically verified, experimentally verified, theoretically well established law. So there is no problem of consistency or existence of there is no question on the existence of E and B if rho and J are given. So the other possibility is that some of these equations have redundant information, that is, they are repetitive information. They already exist in the rest of the equations. So we would like to fix this problem, and the way we can fix it, that if we look at this second equation carefully, so its second equation reads del dot B equal to 0. This is the second equation. So it means divergence of B is 0. Divergence of something is 0 means something can be written as curl of any vector field. So we call this vector field as a uh, vector potential, right? So I can write B as a del cross A, because this guarantees that del dot B is always 0. Divergence of a curl is always 0. If we plug this value in the third equation, which is del cross E is equal to minus del B by del T. So what do we get? Del T B is del cross A. So if we look, del cross E plus uh, del A by del T equals 0. So now this reads that curl of something is 0. Curl of this uh, vector field is 0, which means this can be written as gradient of some scalar field, and by convention put a minus sign, and the scalar field phi is called the scalar potential. Okay, so E is equal to minus grad phi minus del A by del T. So it means if we know phi and A, we can find E and B, because that was our objective. Now phi is a scalar uh, quantity and A is a vector quantity. So A has three components: AX, AY, AZ, and phi is a one component, phi. So it means now instead of calculating six component AX, AY, EZ and BX, Y, BZ, if we calculate AX, AY, AZ and phi, we will be able to find out A and B. So our original problem of calculating the six unknowns now have been reduced to calculating the four unknowns: AX, AY, AZ and phi. And let's see what the other two equation that we have not used so far, the first and the fourth one. uh, what information do they give? The first equation, if we use, that del dot E is equal to rho upon epsilon naught. So del dot E is nothing but minus grad phi minus del A by del T is equal to rho upon epsilon naught. If I take this minus del square phi minus del dot A is equal to rho upon epsilon naught. So that's the another equation. Let me call as equation 5. And the last one, the fourth one, which we have not used, let's see what does it give. The fourth one is del cross B is equal to mu naught J plus mu naught epsilon naught del E by del T. So del cross B is del cross A now, and mu naught J plus mu naught epsilon naught del T. E is minus grad phi minus del A by del T. So if we do the math, we'll get del dot A times del minus del square A of mu naught J minus mu naught epsilon naught uh, root del phi by del T. Okay, and minus mu naught epsilon naught del 2 del T2. Right. Okay, so what we can do is we can take this term to the left hand side and take everything to the left hand side except the source term, and now take the del common, so we get del dot A plus mu naught epsilon naught del phi by del T. Okay, and we have okay, minus del square A plus mu naught epsilon naught del 2A by del T2 is equal to mu naught J. So that's what we get. This is the equation number 6. So 5 and 6, with the help of 5 and 6, we can actually find out, because you see a sixth equation 6 is a again vector equation, and equation 5 is a scalar equation. So it, in total, if we see combine if we combine the information in 5 and 6, so basically there are 4 equations. 6 has 3 components and 5 has one components, and there are 4 unknowns. Again, there are 4 equations, 4 unknowns. Now if we look collectively 5 and 6, because I will write down, let's say 5 again here. So if we look 5 and 6 collectively, so there are this is scalar equation, this is a vector equation. So 3 and 4 unknowns are there, 4 equations are there, and the 4 unknowns are there, namely ax, ay, az, and phi. So if we solve 5 and 6, so we get the value of a and phi, and therefore we can find out the value of e and b, and that completes our problem, because our main problem was that we had too many equation comparison to unknowns. We had 6 unknowns, 8 equation, but now we have reduced the same problem with 4 unknowns, 4 equations. So now we'll have a consistent solution. So that's the benefit of writing down e and b in terms of the scalar and vector potential, and these equations take this form. Now further, depending upon the cases, whether we are dealing with electrostatics or relativistic electrodynamics, we can use gauges of our choice. Why we can choose gauge the values of a and phi? Because you see that b is del cross a. B is del cross a. So if we talk about gauges, uh, so del cross a, b is del cross a. So if I add, so the question is that and E is of course minus grad phi minus del A by del T. The question is this choice of phi and A unique? Because once I have phi and A, I will have E and B. The question is that I know that for a given charge distribution and the current distribution, I have the unique value of E and B at each and every point of space. I cannot have two values at one point. But the question is or are phi and A also unique? The answer is no, because we can see that if we add anything in A such that uh, it is a, let's say, gradient of some scalar quantity lambda, so what's this second term will lead? Curl of a gradient, and curl of a gradient is identically 0, del cross del lambda, where lambda is a scalar. So this second term will actually contribute nothing to this overall b value. It will remain same, but now a has been modified to a prime, right, where a prime is a plus delta lambda. So choice of a is not unique. We can always add in the value of a any quantity which is can be written as a gradient of some scalar. And if we look for the e value, grad phi, and let's suppose I've chosen a prime in place of a, so this is a plus del lambda. And if I repeat the same story, that in place of phi, suppose I write phi prime. And what is phi prime? The phi, if I add something in phi whose gradient is 0, and we look for the whether the choice of phi is unique or not. Suppose I replace phi is phi prime, where phi prime is a phi plus some beta, right? So if I want to keep my value of a unchanged by changing a to a prime and phi to phi prime, so what does it means? It means that minus of uh, grad beta and minus of grad del lambda by del t should be equal to 0. Only then it will give you the same e. We have changed to a prime, phi to phi prime, such that phi prime is phi plus beta, some beta, but with the condition that this thing should give me value as 0. It means grad beta plus grad del lambda by del t should be 0, or in other words grad of beta plus del lambda by del t equal to 0, which can be thought of as, now since del is del operator, which is having the partial derivative with respect to space only, so this thing can be in general dependent on some time, um, on some time factor, right? uh, and beta will there would be minus del lambda by del t plus some k prime t, where lambda is having uh, time dependence here, right? So what we can do here is we can combine these two terms, and we can, because lambda is also time dependent, so we can write combinedly, we can convert this lambda to some lambda prime. In other words, what I'm to say that we can always convert lambda to lambda prime, such that we have absorbed this time dependence term into lambda itself, right? If we add in this, so we can always convert some lambda prime is equal to some lambda plus some other term, where del t of this other term is nothing but k prime t, like that. So we can always choose that. So we have a freedom of choosing the value of a prime, or a value of a and phi. We can modify it, phi prime by phi plus beta, and a by uh, a prime, a prime is a plus grad lambda, where this condition of course has to be satisfied, beta and lambda. So if we can choose such a pair of beta and lambda which satisfy this, so we can always gauge the values of a and phi. Now the benefit of this thing is that if we look these equations, specifically the 5 and 6, now 5 is still okay, but 6 one is very complicated. It seems to be very complicated equation. It looks clumsy in its in the present form. So if we used two different gauges which are very popular gauges, first the Coulomb gauge, which is primarily used in electrostatics, so which is del dot a equal to 0. We can choose such an a prime or such a so that we get the divergence of a is 0, because I told you that choice of a is not unique. We can always have a prime a plus some grad lambda. So if we have chosen such a for which del dot a is 0, so if we look carefully, the equation 5 uh, gets converted into very simple looking equation. So here if we choose, so we'll get del square phi is equal to rho upon epsilon naught, right? So it is basically gets del square phi is equal to minus rho. So it is nothing but Poisson equation, for which we already know the solution is some 1 upon 4 pi epsilon naught integration of rho by r solution. We have already solved it. It's nothing but Poisson equation. We already know the solution. And the sixth equation become, with the application of this gauge, so this term goes away. So we have I should write, maybe I can write mu naught epsilon naught del t grad phi, um, mu naught j. So this is what the new equation becomes. So we can solve these. Let's suppose this is 7, this is 8. So we can solve 7 and 8. 7 we already know the solution. Once we know the phi, we can plug grad phi here, and we can solve for a, for the in principle, and we can find out a. Now if we discuss the other gauge, which is generally useful in relativistic electrodynamics, the low range gauge. So if low range gauge, or in some of the text it is written as low range gauge. However, this is the, I believe, the correct one, because this low range is different from this, that low range transformation. Okay, so low range gauge is, if we look carefully, this bracket here in the equation 6 seems to be complicated. So if we choose this gauge, if we choose this bracket to be 0, we choose our gauge such that the del dot a plus mu naught epsilon naught del phi by del t is 0. So what do we get? From 6 we get del square a minus mu naught epsilon naught del 2a by del t2 is equal to minus of mu naught j. This is my new lesson 9 equation. And from 5 we have this was our 5. In 5 we use, so this gauge if we use, so minus del square phi minus del t, and del dot a is minus of mu naught epsilon naught del phi by del t, and that is equal to rho upon epsilon naught. So this gives me del square phi minus del mu naught epsilon naught del 2 phi del t2, and minus of rho epsilon naught. So if we look these two particular equations, this one and this ninth and 10th, if we look these two equations carefully, so these look very symmetric equation. Now they don't look like awful equations of 5 and 6 earlier. Under this gauge they are very symmetric, and in fact the operator, if we look 9 and 10, I can also write 9 in, it's called in the form of D'Alembert, right? D'Alembert A is equal to minus mu naught j, and the 10th, this is 9, and 10th is also D'Alembert operator. I can write D'Alembert phi is equal to minus rho upon epsilon naught. So these two equations have the source term in the right with the negative, and we know that when we go from uh, electrostatics to magnetostatics, or electricity to magnetism, we have to replace 1 over epsilon uh, not to mu pi, and the source term is symmetric j and rho on the right hand side, and the left hand side is also symmetric, where this D'Alembert operator del square, which I am calling it, is nothing but what? It is equal to del square minus mu naught epsilon naught del 2 by del t2. So this is known as D'Alembert operator. So now the benefit of this gauge has been that it has reduced the original Maxwell's equation in a very symmetric form, very useful form, where we can remember it very easily, and now we can solve them for a and phi if rho and j are given. So once a and phi is known, all the components of E and B can be known, and therefore we can easily solve any electrodynamical problem. So this is how we can solve some sort of mystery of Maxwell's equations, where we earlier thought that we had larger number of equations than the unknowns, but all the information can be extracted in this way. So that's for solve for the first lecture, and we'll continue some few important interesting things in the next lecture. Thank you.